I am Hina Gear of SCSP. I am honored to introduce our next group of esteemed speakers. Dr. Kim Budil, Director of the Lawrence Livermore National Laboratory and President of Lawrence Livermore National Security, LLC. The Honorable Dr. Shirley Ann Jackson, President Emerita, Rensselaer Polytechnic Institute and former chairman of the U.S. Nuclear Regulatory Commission, and Dr. Maria Zuber, Vice President for Research at the MIT and a co-chair of the President's Council of Advisors on Science and Technology. They will be joined by Dr. PJ Maykish, a Senior Policy Advisor at SCSP, for a conversation on the new frontiers of innovation. Over to you, PJ.
Thank you so much, Hina, and good afternoon, everybody who's here in the room and online. Thank you so much, and welcome to the New Frontiers of Innovation. The purpose of this panel is to explore the future of technology trends that could matter to the nation and to international affairs, and also to think about the innovation ecosystem upon which those innovations take place. That's our simple purpose. It is a complete honor to be able to lead this panel with three of our most distinguished scientists and leaders from around the country. I would like you to get to know them a little bit, so I'm going to do just a touch of intro beyond the bios that are on the papers. And first, I want to talk about their scientific achievements. It just so happens as a nice serendipity that all three of our guests are physicists, like Ash Carter was. We didn't plan that, but it worked out that way as a nice serendipity. Kim Budil was a physicist and also had a strong arc in her experience towards applied science. She found herself focused on high-power lasers and ultra-fast lasers in the NOVA program, which preceded the big breakout that you may have heard about this year at the National Ignition Facility. So Kim has been working in those trenches going back to 1987. So it's a long arc of history there for her. Dr. Shirley Ann Jackson was a physicist focused on condensed matter, and her initial work there at Bell Labs led to her induction into the American Physics Association for condensed matter work. Dr. Maria Zuber, she has been working on geophysics. And so she had a focus on deep laser energy space-based systems, but she's also done interplanetary mapping of the planets closest to us and to asteroids. And so we have three physicists of distinguished backgrounds, and they also happen to be leaders of distinguished backgrounds. And I would like to just bring that out for one moment. Kim is the first female leader of Livermore, and she came up through the ranks to do that, starting in 1987, going from one national laboratory project to the next to be the 13th and first female leader of Lawrence Livermore. Dr. Jackson was not only the first African-American woman to receive a PhD at MIT of any kind, but she was also the first African-American leader of the Nuclear Regulatory Commission, and also the first female leader of Rensselaer Polytechnic Institute. So incredible leadership accomplishments there. Dr. Zuber was the first woman to lead a NASA planetary mission, specifically something called the Gravity, Recovery, and Inertial Laboratory, or the GRAIL project. And for anybody who's familiar with how JPL works, breaking through that ceiling in an all-male environment was quite an accomplishment. And so, in addition to being accomplished scientists, I would just love to give them a round of applause for their achievements as leaders. Yeah, thank you so much. So I would love to just open up so everyone could get a chance to know your intersection with national security background. So just starting down the line, alphabetical, could each of you just share a story about your intersection with national security, either where you felt most connected to national security or something you felt was the highest bar of your achievement there? Kim?
Well, I guess I'll start with how I came to be in the national security community. I came to Lawrence Livermore National Lab as a graduate student, was an experimental physicist, wanted to work on lasers. Livermore was at the heart of laser science and development at that time. Many people say our LLNL stands for lasers, nothing but lasers. So we do other things. Anyway, I knew nothing about national security. I knew nothing about national labs. I was really there to do my dissertation research. And because of the program I was in, I was a student employee of the lab. I got a security clearance while I was a graduate student, and I started to learn about the work that Livermore does in nuclear security. And so I was sort of slowly drawn into understanding how the work that I was doing could be part of this higher purpose and this bigger community. And for me, that was very important. Getting to do great science was really fun and exciting, but the opportunity to contribute to this much bigger purpose really is what kept me at Lawrence Livermore and has fueled my career.
That's fantastic, Kim. Thank you. Dr. Jackson?
Well, the way I got into national security actually came through industry. While I was still at Bell Labs, I ended up on the board of directors of a nuclear utility company that had nuclear power plants. And then on the advisory board for INPO, which was the industry group, the Institute of Nuclear Power Operations, that was set up in the aftermath of the accident at 3 Mile Island to improve the performance of nuclear plants. But that led to, by a rather circuitous route, but led to my becoming chairman of the U.S. Nuclear Regulatory Commission, and which I did for about 4.5 years. So that's where I really entered the national security framework. The NRC licenses and regulates nuclear power plants, civilian uses of nuclear energy, exports of nuclear technology for peaceful purposes, but also works with national security agencies relative to nuclear non-proliferation materials, control, protection, and accounting, and so forth. And in fact, that's how I met Ash initially. And so, I don't know, I always respected him. And as you know, at that time, during that frame, which was when I was at the NRC, he was the Assistant Secretary of Defense for International Security Policy, and as such, was very involved in all things Russia, having to do with securing the nuclear weapons, particularly getting them out of Belarus, Kazakhstan, and Ukraine, as well as with what was called the agreed framework that froze the North Koreans' plutonium production through their reactor program. And then what was called the HEU purchase agreement, the high enriched uranium, where we actually ended up buying 500 megatons of uranium from Russia and blended it down. It was blended down actually by them, although some by us. And then it was used as fuel in nuclear power plants. So I had the responsibility as part of leading the NRC with ensuring how that whole thing went down. And so that got me involved more and more in issues having to do with national security.
Amazing how that's come back to our memory as the war in Ukraine has kicked off.
Well, in addition, I actually went to Chernobyl, and we worked with the Ukrainians because when the Soviet Union broke up, the Russians took the design documents relative to how the plants of the Chernobyl design were, so they didn't know how the plants were really designed. So we helped them reconstruct the design basis of those plants. So I actually visited Chernobyl. I say it probably took 10 years off my life, but here I am. And
Thanks.
Stephanie, I just want to say to you how important it was in my life to have had the chance to know and work with Ash early in his life, but also the great privilege we had when both of you visited Rensselaer Polytechnic Institute when we gave Ash an honorary degree, but he honored us. So I just want to thank you.
Thank you so much, Shirley. Dr. Zuber, your intersection with national security.
Yeah. So I'd like to just start by telling one Ash story, and this was one of the last things that Ash had done. I co-chair PCAST, the President's Council of Advisors on Science and Technology, and we were delighted when Ash agreed to serve on PCAST. And we would go to different events, and I'd be with Ash, and he'd say, well, come here, I need you to meet a few people. And he would introduce me, and he would always say, and Maria's my boss, I work for her now. And it was, of course, very embarrassing, but it just goes to show, like we've heard so many other times today, how Ash just elevated everybody around him to higher levels. And so I'm just so grateful for that. So the way that I actually got involved with nuclear security actually is because the Challenger blew up. Okay, the space shuttle was going to be launching a mission called Mars Observer that was going to go to Mars, and after the Challenger blew up, the shuttle program was delayed for a long time, and the mission went way over budget. That had to be rebuilt, and so they decided to open up. They deselected some of the instruments on the spacecraft and opened up a competition for propose an altimeter to go to Mars. And what had been on the spacecraft before was a radar altimeter. And there was, during the Reagan administration, investments in Star Wars laser technology. And I was one of the people who helped declassify Brilliant Pebbles laser technology, and said, wow, if I can let the DoD do my R&D, I could send this really cheap instrument to Mars that will outperform what flew before. And so I wound up being competitively selected for an instrument to go to Mars 2 years out of grad school. So, and the rest, I think, is history.
Fantastic story. Thank you so much. Maria, while we're with you, we'd love to turn to the purpose of this panel and think about, help us see through your eyes, the future of tech. Technologies that you think either in theme or specific categories that are strategic in their nature, and where do you see the big trends going personally?
Okay, so let me talk about a couple of things. We haven't talked about space too much today, and so I'll just mention that what I'll call the democratization of space. So right now we've got the private sector successfully launching and operating surveillance sensors, both visual for observations. We've got methane sat launching, and so we live in a world now where very high resolution observations from space are no longer going to be classified. It's going to be the great opening, and quite frankly, there's going to be no place to hide. Okay, so things that used to be hidden will never be hidden, and societies that are used to being very open, I think, are going to benefit from that. And very closed societies that have tried to hide things are going to learn that that's going to be more difficult to do. So I think that actually plays to the advantage of the United States, where which has had an open society. I'll give one more example. We've talked a lot about AI today. Maybe have talked a little bit less about AI and the life sciences, and we talked about bioterror, but there's some actually really great positive things that can come out of AI in particular and synthetic biology, because many things have evolved in nature, but like a lot of things that we might want to have haven't yet evolved, but perhaps they could be designed. Okay, so it's, imagine designing a microbe that could cause plastics to decay from the environment. Thinking about the nitrogen fixation cycle so that we could either have plants that self-fertilize or think about fertilizers that can be designed in much, much less energy-intensive processes. And of course, enough food to feed the world is another issue. So those are just a couple of, just a handful of examples where I think this can be very good for us.
Thank you so much. Shirley, MIT ×3, you go to Bell Labs, you lead the Nuclear Regulatory Commission, You lead R&D at RPI for years. Where do you see the tech going of our day?
Well, interestingly enough, I started as president a center, the Center for Biotechnology and Interdisciplinary Studies. And the whole point had to do with marrying engineering, the physical and computational sciences with the life sciences. And obviously, AI and machine learning and so on are all part of that computational piece. But what I really would like to talk about are a couple of aspects of that marriage that really relate to national security in an interesting kind of way. One of them has to do with the role of neuroinflammation in neurodegenerative disease and understanding what drives that inflammation. There is some suggestion that disruption in circadian rhythms are linked to this kind of neuroinflammation. And you say, well, what does that have to do with national security? Well, if you have a warfighter is in a conflict, that person is not exactly sleeping your standard 8 hours a day. And so these kinds of things in terms of what can degrade their functioning, obviously in the moment, but importantly down the line, as for what they do for the country, what happens to them after the fact. And so this is the kind of thing that this work is meant to do. But having said that, people don't really understand at a microbiological level, although they're beginning to probe that, what happens, what genes are expressed or suppressed as a consequence of certain kinds of stresses, and therefore what is implicated. And are we then, with some of our newer techniques, CRISPR being one, to affect and change the propensity for this kind of neurodegenerative disease formation to progress. So that's one example. A second has to do with climate change and the environment, but particularly having to do with fresh water systems. And we actually have a project at the university at Rensselaer called the Jefferson Project. But it really has to do with multi-omics, and this is where AI and machine learning come into play, which has to do with, we're seeing more and more these algal blooms forming. And they're called harmful, but it's somewhat of a misnomer because they're not harmful unless they create so-called cyanotoxins. And there are really people now beginning to understand, again, certain gene expression that's associated with cyanotoxin formation. But the real question becomes, how does the microbiome change in bodies of fresh water in particular, as a consequence of the biota in that body, circulation models, fluid motion, environmental effects, including pollution and so on. And so this particular project is looking at that, and now it's being extended to other lakes. But the point being, again, what can we understand about how the stressors link to genetic changes, a kind of de facto gene editing? And are these things heritable if they are things that happen to living systems? And so if you can understand how they get expressed and or how they get changed, the genes, then there is the question of what intervention strategies one can have. And so these are some of the ways that, new approaches to looking at biological systems, both in the natural environment as well as in humans, become increasingly important. But it is what people call a multi-omics problem. Because if you look at the whole, going back to the issue I mentioned in the human body, Some of this also gets related to infectious disease and inflammatory response. How does the so-called extracellular matrix, that's the kind of niche within which the cells exist, how does that change, in the presence of certain kinds of stressors? And again, can we change?
So this convergence. Between
But
them.
it also links to pathogen formation. And can pathogens, be changed, or their binding to the cell change?
For better or for worse, potentially.
For better or for worse, because you cannot get to the cell without going through the extracellular matrix. And so all of these things come into play. And so when people think about bioweapons, and then this is my last comment here, many times we're thinking about the sort of instant weaponization of a pathogen. But had COVID, the coronavirus that caused the global pandemic, been designed, and I'm not arguing that one way or the other, it would have been a de facto, because there are two ways things can have an effect. Of course, we think about how many people die at once, and we did have over 1 million people in this country alone die. But the real point is, if we have worried about societal disruption because of social media. But what caused greater societal disruption than the COVID-19 pandemic? And that then offers an opportunity space for an adversary to come in. So I'll stop there, but I think you get my point.
That's a great picture of how this could go into the threat space in national security.
Exactly.
Kim, we've been so amazed at Livermore when we've been out there. Everything from the breakthrough that everyone's read about, but also the creation of things like self-driving labs that autonomously do scientific discovery, your experts at Z Group, everything. Where do you see the future of tech? If we were to just look through your eyes, what do you see coming? What do you think has the most strategic significance?
So I think I'm going to pick up on the themes that both Maria and Shirley brought forward. The pace of innovation is accelerating because of the tools we have at hand today. So we've talked a little bit today about AI and machine learning. It's not magic, it doesn't solve your problems, but it gives you the ability to use massive amounts of data in ways that were not conceivable 10 years ago. So in the biosciences, the nexus between large-scale, high-performance computing, so now we're citing an exascale computer, 2 exaflop computer, with things like data science, AI, and machine learning, and engineered platforms that allow you to take new kinds of data, are going to allow us to make progress in biological sciences at a pace that we've not seen before. I've warned my sons, I plan to live to be 150. Things are changing so fast that is, these very long lifespans with good quality of life are within reach. We did a project during the pandemic to show the power of computing for drug discovery and design. Someone mentioned that earlier. As new variants of the COVID virus emerged, antibody treatments that were designed for the prior variant didn't work with the new variants. In a span of 2 weeks, our researchers were able to redesign antibodies to a new variant of COVID. And the long pole in the tent was actually handing them off to a company and testing them for efficacy. But they were in market within a few months. So you can take this laborious process of discovery of therapeutics and countermeasures from a decadal-long process where most things fail to potentially weeks to months. And think about the implications. Think about orphan diseases where there's no economic incentive to really create therapeutics. If you can make that timeline short enough, you can change the game on that. So things that are killers around the world today could be eradicated. I think the other thing that we're getting in technology space is the nexus between, again, computing and both the scale and the ability to use things like AI for design optimization and advanced manufacturing technologies. So you can now architect materials with really unique properties and build structures that were inconceivable before things like additive manufacturing were available to us. This gives you the opportunity to create technologies that it would be hard for humans to conceive of. The computer can really help you explore the design space in a way that humans don't. And I would be fired if I didn't talk about fusion. So, we have, as a nation, invested over 6 decades in the science and technology that brought us to the breakthrough at Livermore from last December. So the first time in the laboratory where we achieved more fusion energy output than energy into the experiment. And this is a moment for us to decide if we are going to go all in on what could be one of the most game-changing technologies the world will see in the next several decades. Part of that story is incredible persistence. It's a nexus between large-scale engineering. The laser system that we use is an absolute engineering marvel. Innovative ideas and modeling and simulation to help drive the whole system along. But, what it really is at heart is a story of patient public stewardship of a really hard problem that has very significant national security applications and implications. And so, I think continuing to invest in big science, in science that bridges both the open community of innovation and the national security challenge is going to be really important. And if we're going to capitalize on that breakthrough, it's really going to require a new kind of innovation ecosystem that brings public and private sectors together in new ways.
That is a fantastic segue to what I would love to get your thoughts on. And then I would love to turn over to the audience for any questions you may have of our panel. Something at the Special Competitive Studies Project that we've been working on is how would you change the innovation ecosystem? Because ultimately we're in a competition between international systems. One happens to have the second largest economy, happens to be authoritarian, happens to be designing against the United States and its national security apparatus. If it's a system versus system, and you were to take a step back, what are some fundamental ways you would tell the president how we should change our innovation ecosystem? Maybe maximizing public-private, maybe scaling something you've seen work. Let's start with you, Kim.
Sure. So one thing I would say, and it's a little parochial, but I still think it's true, is to go back to basics. So the national labs were created in the wake of World War II to steward capabilities, R&D innovation ecosystems that would be difficult to maintain within the government, but that could be close enough to the government that we could understand the problems and challenges and always be creating capabilities out ahead of need. And so over time, we've lost the idea of that partnership, where these organizations can bring together academia, industry, nonprofits, philanthropies, government entities in new ways, work in the public interest, and really tackle these big, enormous challenges. And the National Lab System, the Department of Energy National Lab System, is the envy of the world. I mean, we've had groups come from China to try to find out what's the secret. How do you create these kinds of institutions that can do science at a scale that is hard to achieve in any other environment? So I think that's one thing. Remember what the ecosystem is supposed to look like. Yeah. And the second thing was discussed on some of the earlier panels. We've created an enormous range of barriers and obstacles to moving fast. And the strategic advantage in the 21st century is speed, right? There are many smart people around the world. There's lots of knowledge, lots of great ideas, lots of tools and technologies. It's the pace at which you can innovate and take advantage of those tools and technologies that'll create strategic advantage for the United States. So getting out of the mode where you have to understand in great detail exactly how things will work out before you start, and allowing people to take calculated risks, to be more technically ambitious, to aim further over the horizon, I think has got to be a part of our ecosystem going forward.
Fantastic. Shirley, if we were to update Endless Frontier, 1945, dust it up a bit, it was a while ago. If you were to dust it up, what would you share to the president?
Well, a couple of different things. First of all, let me pick up on something Kim said. We talk a lot about innovation, but in the end, there's no innovation without innovators. And as you heard through multiple panels today, talent, human capital, is a real challenge. And so one of the things that would need to be embedded has to do with just that, talent attraction, management, and retention. And that then, to me, requires two things. One is, really grappling with this question of immigration, particularly as it relates to science and technology talent and to come up with new models. Now, I have a few ideas, but because I'm on the Defense Science Board, I can't talk about it yet. But that's one element. But the other is, and I think we have to be careful because there's a lot of polarization in the country. But if we talk only on one side, we talk as if there is no native talent in this country. And that does not help in terms of whether people feel left out, whether they feel they matter. And this doesn't have to do particularly with any particular group. It has to do with all of us. And so I think this issue of a balanced approach to talent, attraction, development, and retention. And I'm old enough that I remember the NDEA, the National Defense Education Act of 1958. And its focus was on just that. And so Kim talked about going back to basics. One has to go back to basics, but now with the opportunity to have this balance of attracting and retaining exquisite talent from abroad, but identifying, attracting, nurturing exquisite talent domestically. And we've got to do that. And so that's one. The second has to do with new models, which may mean a regeneration of models for how one supports research. Because, you pick your poison, satellites, your example, I should say, mRNA vaccines. These things don't come out of thin air. The whole mRNA technology depended, yes, on advances in biology, but it also depended on advances in material science. It depended on advances in manufacturing. And so all of these things and others had to come together. And to have that and that understanding that you don't, that it takes a comprehensive approach that supports a broad range of activity is very important. And then finally, and this is more DoD specific, I would like to see the DoD labs open up more in the sense of some of our national labs and to figure out ways for those who either do not have or cannot have security clearances to nonetheless participate in open research. So these are some of the thoughts.
This is something our leader, Ili Balrakhtari, talks about sometimes as a front door, back door organization where you can bring talent into the lab, and something we've seen Livermore doing. And we thought about how would you scale that to achieve what you're saying, Shirley?
Yep, I'm gonna just friendly interjection because you're right on. If our scientists and engineers and researchers are gonna support national security and be the very best, they have to participate in the open science community. There's no other way to do that. So they have to work with the best people in the world. They have to test their mettle out in that open community. And then we bring the best people, tools, capabilities, and ideas into the national security community to keep that ecosystem live and vibrant. And our national security really does deserve the best. So having that view of, open science, engaging with the broad community where, so much energy is being generated, but always with an eye toward what are the implications of this tool or technology or idea for the national security, and how can I use that, again, to advance the cause for the United States is really important.
Fantastic.
Sorry.
So Maria, would love to ask you the same question. How would you update NLIST today? How does the ecosystem need to change? And then let's take some questions from the group.
Yeah, so let me make a structural comment. All the systems of the partnership have to work well together. And you could ask the question, how well is the federal government positioned in terms of its workforce to be able to address our needs and our aspirations related to national security? And I would argue could be better, could be improved. And so I think we need to make it easier for people from either universities or the private sector to come and do a stint in the federal government. Because right now it's very difficult to do. So we have IPAs. We need to make that easier so that it can be more of a revolving door and shared experiences, which I think is going to be to great benefit. And another thing that I'll mention that actually wasn't part of the initial Endless Frontier specifically is, Shirley talked about immigration getting, talent from all over the world. We got to do a better job of tapping the talent within our own country. Okay, so let me give you the example of the public universities. Okay, so every state has a flagship university that's an R1 university that's pretty darn good and has a lot of really smart kids in it, and we need to be able to tap into that talent. Okay. But the states, many of the states have been cutting down their investments in those state universities to the point where some of those investments are now in the single digits, okay? And you can't take tuition revenue and plow that into supporting research. I mean, you just can't. And so it used to be that the publics would have some advantage over the privates because they could pay for renovating labs and technician support, and now all that's been chiseled away, and let alone the increasing cost of compliance in order to be able to do research. So these universities, which are great universities, are getting priced out of the game because they just can't afford to play.
And if you would just let me do a +1 to what Maria said, and I will add that it takes real infrastructure in the university to do high-end research. And frankly, the federal government used to support more of that at a higher level, not to mention the support of states for the state universities. And so it has to be a balanced picture, because if we want to support students, they have to come to do something. And in order to do research and to be educated in that way, there's an infrastructural issue as well as the cost of compliance.
Yeah, and we need to up our infrastructure investment for students and researchers at the public universities, at the private universities, and at the national labs. I mean,
That's
we
right.
all need infrastructure so that we're able to really work at the state of the art.
Absolutely.
Thank you so much. This is the beginning of our agenda for updating Endless Frontier right here. Questions? We have a few minutes. Would love to get open to the floor. If you have a question, please raise your hand. We have a team with microphones that will come to you. I see Jafar on his way to someone right now.
I'd like to thank the panel very much for all of your commentary and for your time. It's been absolutely inspirational to look up and see the three of you, four of you, sir, as well. But as a young female who started in science and not in national security and then found my way over into national security, it was a theme that I noticed for all three of you. That love of science was something that you had endogenously, and then you found your way through exposure opportunities into this sector that we all know and support. So can you talk a little bit more about how to create those opportunities for people who have that love of science so that they can also develop a passion for the mission? Thank you.
So I think there are a couple things I usually recommend. Of course, I recommend there's fantastic internship opportunities in the national laboratories where students can come and work with our researchers and understand about our missions. When I talk to students, STEM students in universities, I also talk about working in the government. I think it's incredibly important that we have scientifically literate people in the government who could really understand the world we live in. And I think that's another great way for people to understand just how complex policy is and how hard it is for the government to grapple with highly technical issues that undergird many policy questions. So I think those are both great ways. And I think it's incumbent upon those of us who do science in the national security community to get out and engage, help people understand the work that we do. I think for us, there's a mythology around our laboratories that all our work is classified and the gates are tall and no one can come here. And the vast majority of our work is unclassified. And we have lots of students and postdocs and whatnot in our environment. That's what really keeps the atmosphere lively and energetic and builds the next generation of national security researchers. So I think both of those, if you have an opportunity to work in the government and serve, please do. Come to a national laboratory and learn about what we do, or invite researchers from the national security community to come and talk about their work.
I would like to see the government open the doors a little more and open them earlier to young people at an age and a stage where one would not expect them to be able to make a contribution, but they can. And these students, the ones we have in places that my colleagues have been, are brilliant, and they're very focused, and they can make a difference, and they want to work on hard and challenging problems.
Yeah, that's a great question. And so it's so frustrating because of the fact that much of the work is classified, you can't convey to people, and we need to do a better job of conveying people, that the work going on in support of national security is absolutely first-rate science and technology that is completely state-of-the-art, and it's a lot of fun. And so, one of my responsibilities is I oversee MIT's Lincoln Laboratory, and I say, Lincoln Laboratory, imagine James Bond's Q with $1 billion budget. That's what it is.
Sign me up.
Exactly.
That's right.
We have room for one more question. Anyone at all in the room with a question? Otherwise, what I would love to do is thank the three of you so much, not only for what you've done for U.S. power and national security. Asher, we have one more? Sure, go ahead, Asher, please. It's hard to see up here, so I'm depending on you to identify.
I just had a question about Dr. Budil's comment on having folks engage with the open science community and how you're balancing that with the ideas behind certain aspects of national security that you want to be classified and to retain a competitive advantage. And this maybe relates to points that were brought up by Dr. Schmidt and even Dr. Jackson here about biorisk and these sorts of ideas. I'm wondering if you have any thoughts, on finding this balance, or whether you think just going with the open science is a good enough balance.
So, part of what we offer, part of what we do is we cultivate a community that understands both the open science and the national security implications. So, our researchers are prepared to make those choices. They understand what to talk about and where to step back. The biggest challenge is that we can't put, fences around information or ideas, right? In many of these fields, bioscience is a good example. They're inherently unclassified. So there's a huge amount of information on the street that has very significant national security implications. It works in the other direction there, where we want to get as much understanding as possible of what's going on in the community, what are the possibilities of the technology, so that we can begin to think about it through this national security lens on the other side. So
I'll just make one quick comment, which is we do the best job we can with protecting the information we think is most sensitive.
Yep.
But in the end, we have to compete.
Maria?
That's good.
Yeah. No, I don't have much more to add there, except to say that every once in a while you lose a little bit, but look at how much you gain. And looking at the gain versus the loss is a very important thing to do. So.
Thank you so much for that question. Thank you, panelists, so much for just beginning this conversation about how to change the innovation ecosystem, where tech is going. On behalf of the Special Competitive Studies Project, everybody who's here today, thank you for your contributions to science, to leadership, and tech powers hollow without you. So thank you so much.
Thank you. Thank you. Thank you.